Hello, this is Jack Jackson. Today we're going to be talking about graphing exponential functions. So we're going to talk about the characteristics of the graphs of exponential functions. So to start things off, let's take a look here at this particular example here. Actually, two examples. F of x equals 2 to the x power, and g of x equals 1/2 to the x power. Notice by properties of exponents, 1/2 to the x power is 1 to the x over 2 to the x, which is 1 over 2 to the x power, which could also be written as 2 to the negative x power. And that should give you some indication about how these two functions compare to each other. So what I want you to do is to get two colored pencils out. Hopefully you can already printed out this set of notes maybe, or just do this on a piece of graph paper, and figure out the y values that go with these particular x values that I have picked here in the table, and then graph the two functions on this and tell me how they compare to each other. So go ahead and do that now. When you're done, come back to the video. Press pause now. Well, let's look at 2 to the x power. We'll start with the easiest one. 2 to the first power is 2. 2 to the second power is 2 times 2, which is 4. 2 to the third power is 2 times 2 times 2, which is 8. And notice that every time we go up 1 on x here, then we're multiplying by 2 on y. So this goes 2, 4, 8, 16, 32, 64, and so forth. This pattern continues when we go the other direction. So if we're going down 1, we're dividing by 2. So 2 to the 0 power is 1. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1 over 2 squared, which is 1/4, or 0.25. 2 to the negative 3 power is 1/8, or 1 over 2 cubed, 1/8, which is 0.125. And then 2 to the negative 4 is 1 over 2 to the 4th, which is 1/16, and so on. Now let's take just a look at the graph of that particular one. That's the purple one down here. So let's see what we can get of those points to fit on this window. So here's 2, 1 right here. Then we have 2, 4 right here. 3, 8 there. And I think 4, 16 will also fit. There it is. And then we have 0, 1 here. Negative 1, 1/2. Negative 2, 1/4. Negative 3, 1/8. Negative 4, 1/16, and so forth. So as we go further and further to the left, the y values get closer and closer to 0. They're getting half as big each time as we move 1 to the left. As we move 1 to the left, the y gets halfway closer to the x-axis. So notice it'll never actually hit the x-axis, okay, but it will get as close to the axis as we want to get. So it goes all the way to, but not including the x-axis there. So we say that the graph has a horizontal asymptote on the left side. Now this is one connected graph, and it's increasing concave up here. And it actually goes on, we should put arrows really on both ends here to indicate that it continues in the same fashion, still approaching the asymptote on the left. At some point it's so visually hard to tell it apart from the x-axis. But on the right side, it goes up forever, increasing without bound. Now, if you notice, when you look at it in this last form, when you say 2 to the x power and then 2 to the minus x power, you can think of this as just changing x to minus x, and we know what that does is change the sign on the x. So I don't have these lined up pre-image to image, but if you think of it that way, the pre-image point, negative 6 1/64, is now down here. The image point is 6 1/64. And for example, 4/16 is the pre-image, negative 4/16 is the image. And so what happens here is you get a reflection over the y-axis. And so no surprises there. It looks like the dark blue graph here. Okay, so 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared is 1/4. 1/2 to the third power is 1/8, and so forth. So every time we go to the right one, we're multiplying by half, or going halfway down closer to the x-axis, closer to y equals 0. And when we get a -1 here, 1/2 to the -1 is just 2. And 1/2 to the -2 is 2 squared, which is 4. And so forth. And you can see the graph there. So notice when we have a base bigger than 1, we're going to get this increasing concave up shape here. But when the base is less than 1, we get the decreasing shape here. They're both concave up. They're both connected, continuous. And they're both domain all reals, and both range only the positives. So remember that a positive number to any power is positive, so the output of the function f of x or y equals b to the x for any positive base is always positive. So the graph is only in quadrants 1 and 2. Now, if the power is positive, okay, or the base is positive, and the power takes on negative values, that should not say base is positive, but I should say more the base is greater than 1. So if the base is greater than 1, like in the y equals 2 to the x power, and the power takes on negative values, as we go further and further to the left, the y values get smaller and smaller, approaching 0, so it has a horizontal asymptote on the far left. We also have already talked about this idea that we're just switching the x to minus x, so that's going to reflect over the y-axis. Now, see if this pattern holds, and see what you get for some of these examples here. So y equals 3 to the x, y equals 1/3 to the x, y equals 4 to the x, and y equals 1/4 to the x. Graph all 4 of those on this grid here, and use 4 different colors. Okay, so go ahead and do that now. When you finish, come back and we'll check your answer. Press pause now. So here's what the graphs look like. We'll check a few points. Let's take the aqua colored green, y equals 3 to the x. So notice all of these are just a base to a power, and they're positive bases, so any base positive number to 0 power is 1, so notice they all go through the y-axis at 0, 1. So the basic, that's one point that these basic exponential functions will have in common. That is, if it's just a base to an x power. Okay, so if you have 1 here, you get 1, 3. That's going to be right here. Then you've got 2, 9, and 3 would go up to 27, which is off the screen. And then you go here to 1, -1, 1/3, -2, 1/9, -3, 1/27, and so forth. So it's here. 4 to the x is very similar. 0, 1, 1, 4, right there. 2, 16, right up here. And then it goes on up from there. -1, 1/4, -2, 1 16th, and so forth. The ones with the bases that are between 0 and 1, they're the ones that are going to be the decreasing ones. Again, they still go through 0, 1, but for example, if we put in x is 1, we get y is 1/3 for the green one, which is right here. X is 2, y is 1/9 here, then 1/27th, and so forth. And if you get x is -1, you get 3 for an output. X is -2, we get 9 for an output right there, and so forth. And similarly, we see for the 1/4 of the x, the red graph. So let's look at a couple of characteristics. So notice that b to the 0 is 1 if b is not 0. So all these most basic exponential functions will have a y-intercept of 0, 1. We're not going to allow a base of 0. Okay? And so if the base is bigger than 1, the function's increasing. If the base is less than 1, the function's decreasing. Now remember, we also have a property that 1 to any power is 1. So 1 to the x is 1 for any power x. So if we have a base of 1 and we just have the function y equals 1 to the x, that really just degenerates to the constant function y equals 1, which is a horizontal line. So we're not going to count that as being a legitimate exponential function because really it's just a constant function in that case. So we will not allow a base of 1. Now if you allow a base that's negative or 0, then we've got an even bigger problem because then we have problems, because remember, when you take a 0 and raise it to a power, or negative for that matter, where the power is negative, well, if you raise 0 to a negative power, it's undefined, or 0 to the 0 power is undefined. So we have things that are undefined there. When we have a negative base and we raise to a power that's irrational, or to a power that's a fraction with an even denominator, then that's going to be undefined. So if we allowed a negative base here, we'd end up with a function that's just full of holes. It would have infinitely many holes there. That's just a big mess. So we're not going to allow that either. So that only leaves us really two possible cases then to consider, and that's the base bigger than 1. That would be like the y equals 2 to the x example we had, or a base is between 0 and 1. That's like the example y equals 1/2 to the x. So all the basic characteristics within these two cases are basically the same, and so let's take a look at what happens. And I'm going to generalize a little bit by what happens if you have a coefficient now of y sub 0. And there are three good forms of the formula that we're going to be talking about. We've mainly been focusing on this first one, y equals y sub 0 times b to the x power. We looked at that in the first section. It also turns out that the base is 1 plus the rate of growth, the percentage rate of growth, so we can also write the b as 1 plus r. We can also switch to a very special number e for a base, and we'll talk more about this when we talk about compound interest. But the base e is a naturally occurring irrational number. It's close to 3, so it's a number bigger than 1. It's about 2.7 something. Okay, and if you change to this base e, then it picks up a coefficient k in front of the x. So you see that e to the k and b are the same thing. So b is 1 plus r, and b is also e to the k. Now for the examples below, we're going to let the coefficient here be positive, and so we get 0y sub 0 turns out to be the y-intercept. Okay, so here are our basic two setups. We have exponential decay and exponential growth. We have growth on the right when the base is bigger than 1. That corresponds to having a positive value for r, and it also corresponds to having a positive value for k. The domain is all real numbers. The range is from 0 to infinity. It's continuous. It is increasing, concave up. It is a one-to-one function. It has a horizontal asymptote of y equals 0, the x-axis on the far left. Okay, and of course a y-intercept of 0, comma y sub 0, which at this point we're assuming is a positive number. That's called exponential growth. On the other hand, we could have exponential decay. That happens when the base is between 0 and 1. That happens at the same time the r is negative and the k is negative. And the characteristics you see on the graph, some of them are the same. It's still domain is all real, so still the range is 0 to infinity, not including 0. In other words, only the positives. It's still continuous, and it's still one-to-one, and it's still concave up, but this time it's decreasing. It still has a horizontal asymptote of y equals 0, the x-axis, but this time that happens only on the far right of the graph. Now, I want to compare and contrast exponential functions with power functions. In our first section of this unit, we compared exponential functions to linear functions, and we found there was a lot of similarity in the way we could develop them, but exponential functions were basically just one level higher in the order of operations on every piece of the way we developed it. But if we think of it in its most basic form, there's an obvious connection between the form of the formula for power functions and exponential functions. In power functions, we just have a base and an exponent, the most basic ones. And for the most basic exponential functions, look what we have. We have a base and an exponent. The same thing in both cases. But the difference in the two is that one's constant and one's variable, and which one's the variable is different in the two cases. So in power functions, the base is the variable, and the constant is the power. So for example, like f of x equals x squared would be an example of a power function. In exponential functions, it's exactly backwards. We have a constant base, and the variable is the exponent. And so, for example, f of x equals 2 to the x power would be an example of an exponential function. Notice exponential functions are actually named after the form of the formula, because where is the variable? The variable is in the exponent, and so that's what they're named after. Now, by the way, if both the base and the exponent are constants, then the function is actually a constant function. Okay? So it's neither exponential nor power function. If both the base and the exponent are variable, like y equals x to the x power, then that's a function that's neither a power function nor an exponential function. We're not going to really study that one in this class, but that is something that's neither a power function nor an exponential. So anything that we know about the power functions or exponentials do not necessarily apply to this function, y equals x to the x. So notice both power functions and exponential functions in their most basic form have a base and an exponent. One's constant, the other's variable. The difference in the two is which one's the variable. Power functions, the variable is the base, power is constant. Exponential functions, the base is a constant, and the variable is the exponent. So when you compare and contrast these, well, we look at the shapes. Well, we've seen that there are basically two basic shapes. Here they are for the two basic shapes for exponential functions. We can have the exponential decay function there that's in red on the left, and the blue on the right is the exponential growth function. But power functions turn out to have lots of different possibilities. If you go back to our power function notes, you'll see there are actually 11 different possible graph shapes, depending on what the value is for that constant power n. Okay? Now, in general, the graphs of exponential and power functions are quite different, but if the power is a number greater than 1, and the base is a number greater than 1, and you only look at the first quadrant, then the graphs have some things in common. For negative values, they're going to be very different, if they even exist for the power function, if the function even exists there. But it turns out that in the first quadrant, they're very similar. They're increasing concave up. But it turns out that exponential growth functions eventually exceed the growth of power functions, regardless of the power. So to illustrate this, let's look at an example. So we're going to let f of x be x to the fourth, and g of x be 4 to the x. And we're going to graph these on the same window. So let's take a look at the graph. Here we go. And so we see, well, in this view, you'd say, well, they don't really look that much alike. I mean, the y equals x to the fourth has some y-axis symmetry. It's decreasing, then increasing. It's got a minimum. It actually touches the x-axis at the minimum there. So it's decreasing concave up in the second quadrant, increasing concave up in the first. In the second quadrant, in both quadrants, the exponential is increasing concave up. So it has an asymptote here on the left. So in the second quadrant, they don't look anything at all alike. But the first quadrant, there's some similarities here. So if we want to look at a different view where we're just looking at the first quadrant, oh, okay, these are a little more similar. Now, where do they cross? Well, actually, if you look back at this picture, you see they cross at a negative value here. That is approximately negative 0.766664696, comma 0.3454791638. How did I find that? Well, I just graphed these two things. One is y1 and one is y2, and did a calc intersect on my calculator. So why don't you try to verify that here in a minute on your calculator. Now, the other two places we could find or at least we might stumble across, or we might be able to see these are exact values. Now this one here, this one in the second quadrant, is actually an approximation of the point of intersection, and there are no algebraic techniques for this, for finding these points. Your techniques for solving power function equations that we've already studied do not apply here. They don't work. And the techniques that we're going to study later for solving exponential equations exactly, they don't work either. So there's no really algebraic way to do this. The only way we can do this is with some numerical approximation technique like the calc intersect thing that's built into your calculator. Now this one is rather obvious when you think about it, that they're going to cross. It's when x is 4. We're saying we're trying to solve x to the fourth equals 4 to the x, and if you put in x is 4, then it's clear that it's going to work because you get 4 to the fourth equals 4 to the fourth, which is obviously true. That's 56. The one that's not as obvious, but once you see it, you can tell it's exactly right, is 2. Because if you put in 2 to the fourth power is 2 times 2 times 2 times 2, which is 16. And 4 to the second power is 4 times 4, which is also 16. So they both go through, they cross each other at these 3 points. You can see the one in the second quadrant right here in this picture, and actually you can see the one at 216, although it's hard to tell exactly where it is, where they cross right here, but it is right here at 216. In this version, of course, you're not going to see the second quadrant, but you do see this point of intersection at 216, and you see the other one at 2,256. So notice we've got a definitely non-square scale. This goes from 0 to 400 on the x, on the y, but only 0 to 5 on the x. Now, in this view, if you look here at the beginning, the exponential is above. Remember, it starts at 1, and the power function started at 0, so it was on the top. But then here at 2, they cross over, and so the power function is dominating for a little while. But then they cross over again at 4, and now the exponential function's back on top. Well, look what happens when we zoom out a little further. If you zoom out further, like we just go from 0 to 10, and we get high enough to see where the exponential goes, look at these points way up here, and look where the power function is. X to the fourth is way down here in comparison. On this scale, it looks like it's pretty, relatively at least, pretty close to the x-axis compared to how far up this is. Okay, it's over 1 million high, right in here. And yet this is still much smaller than that. So this happens in general. Okay, it may be that the power function may be on the top for a while, but if you go far enough out to the right, at least for these basic power functions and basic exponential functions, the exponential function is going to grow faster eventually. So if you've got an exponential growth function, it's going to eventually outstrip any power function. Of course, we make the power bigger, then it's going to be even bigger here, but it's still not going to be enough to catch up with the exponential function once it crosses over that last time. So they may or may not cross each other, but if they do, that last time they cross, the exponential is going to be on top, and it's going to be on top from there on out. And not only is it going to be on top, it's going to be way ahead eventually, because it just picks up speed faster and faster and faster, much faster than power functions are. Now let's apply some of our transformations of graphs to exponential functions. Make this a little bigger. Okay. Well, let's start with the basic function as y equals b to the x. We can first transform the function by replacing y by y divided by 0. Now if you solve that, that'll be y divided by y sub 0 equals b to the x. If you solve for y, that's y equals y sub 0 times b to the x. If you think about it, this is exactly the same form that we looked at back when we were in our first section on this unit, when we were developing this parallel to the linear functions, and we see that y sub 0 is, of course, the y-coordinate of the y-intercept. But by thinking of it as taking y equals b to the x and replacing y by y divided by y sub 0, we can think of this as a vertical strain, a vertical stretch, or squish it. So it's expanded if the absolute value of y sub 0 is greater than 1, and contracted or compressed if absolute value of y sub 0 is less than 1. Now, if y0 is less than 0, if it's a negative number, this is also going to give us a flip over the x-axis. But either way, we see that the y-intercept is now 0, comma y sub 0. Again, if we put in 0 for x here, b to the 0 is, remember, we're not allowing b to be 0, so anything else to the 0 power is 1. So b to the 0 is 1 times y0 is y0, and so y equals y sub 0 when x equals 0. So the y-intercept is 0, y sub 0. Okay, so let's look at a few graphs like that. Here are just a few examples. And I've got a few of these with the negative y sub 0 also. So this dark blue one here is 1/2 times 1/5 to the x. Well, 1/5 to the x, that's a base less than 1, so we're going to see that exponential decay pattern, our decreasing one. But now instead of everything's going to be half as tall, so instead of crossing here at 0, 1, now it's going to cross at 0, 1/2. And again, that 1/2 is your y-coordinate of your intercept. And every time we go to the right one, we're going to be multiplying by 1/5 still. Every time we go to the left one, we're going to be multiplying by 5. So that's 1/2. Multiplied by 5, you get 2.5, which is here, 5/2. Multiply that by 5, you get 25/2, which would be 12.5. That's going to be a little off screen there. How about the maroon one next? That's 3 times 2 to the x power. 2 to the x, of course, would go through 0, 0, 1, and you go to the right one, you multiply by 2. Okay? But now this 3, it means we're going to stretch it all vertically by 3. So instead of going through 1 here, now it's up at 3. Instead of being 2 here, it's now up at 6. Okay? And so everything's multiplied by 3. So at negative 1 instead of 1/2, you get 3 times 1/2, which is 1.5, which is right here. And so forth. Negative 2 to the negative 2 is 1/4 times 3 is 3/4, so you're here. And so we get that graph. Notice the graph does go through 0, 3 on the y-axis, and every time we go the right one, we double our height. So here we're at 3, now we're up at 6. When we go the right one, we'll be up at 12, which is a little bit off screen there. When we go left one, we're multiplying by 1/2, or dividing by 2. So we're at 3 here. Half of that is 3/2, or 1.5. Half of that would be 3/4, which is here. Half of that would be 3/8, which is here. Then 3/16, and so forth. The purple one here, y equals 2 times 3 to the x, is very similar. This one, again, you can see the y-intercept, there's that coefficient there of 2, so 0, 2 is where it crosses the x-axis, the y-axis, excuse me. And you go the right one, you multiply by 3. So 2 times 3 is 6, so it goes through 1, 6. Then you go the right one more, it's going to multiply that 6 by 3, and now we're going to be all the way up to 18. So that's off the screen. Go into negative 1 power. 3 to the negative 1 is 1/3 times 2 is 2/3, so you can see that here. So we took the 2 divided by 3 when we went to the left one. Go left one more, we're dividing by 3 again, so that's 2/9, which is right here, and so forth. Now let's look at some where that coefficient is negative. Again, if you have y equals negative 2 times 1/4 to the x, this takes y equals 1/4 to the x, flips it over the x-axis, and then also expands it by a factor of 2. So again, we can still see 0, negative 2, that coefficient there, negative 2, that's where it crosses the x-axis. Every time we go the right one, we're going to be multiplying by 1/4. Negative 2 times 1/4 is negative 1/2, which is right here. Negative 1/4 times, negative 1/2, excuse me, times 1/4 is negative 1/8, which is right here, 2 comma negative 1/8. And so forth. Every time we go the right one, we're getting 1/4 of the way closer to the x-axis. So notice it still has a horizontal asymptote of the x-axis. It's just always below the x-axis, and it's coming up. So now the function's increasing concave down, coming up toward the x-axis, which it approaches on the right. Let's see. Let's do another one here. And finally, this blue one, notice it's going to go through 0, negative 4. When we go the right one, we're going to be multiplying by 1.5. So negative 4 times 1.5 is negative 6. So that's right here. When we go to the left, we divide by 1.5. Negative 4 over 1.5. Let's see, 1.5 is 3/2. So negative 4 divided by 3/2 is negative 4 times 2/3, which is negative 8/3. That's negative 2 2/3. That's right here, right where it should be, and so forth. Notice as you go, every time you go to the left one, you're going to be multiplying by the reciprocal of 1.5. Remember, 1.5 again is 3/2, so reciprocal is 2/3. So we go to the right one, we're going to multiply by 3/2. We go to the left one, we're going to be multiplying by 2/3. And that's going to get closer and closer to the asymptote on the left. So notice in both cases where the coefficient was negative, you're down here in the third and fourth quadrants below the asymptote, which is the x-axis. Now, sometimes it turns out that we can view a transformation in more than one way. Okay, like we transform the formula, we can think of it as two different ways of transforming the graph. Now, we've seen this before. For example, we take y equals x squared, and we want to write it as y equals 4 times x squared. Well, in this form, it's not clear whether we change the x or y, and we can actually think of it either way. So if we write it as y over 4 equals x squared, then we can think of it as the x squared was left alone, and we replace y by y over 4. So that means what we really do is multiply all the y's by 4. So that's a vertical strain, a stretch, an expansion, so that the x values are the same as they are on y equals x squared, but their corresponding image points have 4 times the y. So for example, 2 4s on y equals x squared, then 2 16 is on the new one. So we multiplied the y by 4. 1 1 is on y equals x squared. It's going to now go to 1 4. But there's another way we can do this. And instead of thinking of it as y over 4 equals x squared, we can think of it as y equals parentheses 2x parentheses squared. So now you can think of it as replacing x by 2x. If you think of it this way, it's a horizontal strain, but this time it's a compression, so it's half as wide, or halfway closer to the y-axis. So if you think of pre-image to image, we'll think of the same two pre-image points, 2 4 and also 1 1. But this time, what are we doing? We're leaving the y's alone and multiplying the x's by a half. So 2 4 leaves the 4 alone, and half of 2 is 1. So that's moving in towards the y-axis this time. Whereas before, when we thought of it up here as a change on x, we're moving away from the x-axis. Down here, we're moving toward the y-axis. How far? Well, halfway closer than we were before. So 1 1 goes to a half 1. Whereas up here, we're thinking of it moving further away from the x-axis. How much further? Well, 4 times as far. So we can either think of this as compressing the graph horizontally to be halfway close to the y-axis, basically half as wide, more or less, or it can be thought of as expanding 4 times as far from the x-axis, basically 4 times as tall. Actually, it's really infinitely tall and infinitely wide, and that's why you can think of it both of these ways. If they actually had endpoints where it stopped, then these two transformations would be a little bit different. But since it goes on forever, you can actually think of it both ways. But notice they were both strains. They were both either stretches or compressions. But there's something interesting about exponents. Because of some properties of exponents, it turns out that actually a horizontal translation is the same as a vertical stretch or compression. So that's kind of interesting here. So again, let the basic preimage relation be y equals b to the x. Now what if we replace x by x minus h? Now we know that this is going to be leaving the y-coordinate alone and adding h to the x-coordinate, which is a horizontal translation by distance of whatever the absolute value of h is. But notice, so this will give us a new formula, y equals b to the power x minus h. That's clearly moved h units horizontally. Okay, if h is positive, because the negative is built in, if h is positive, you're going to the right. If h is negative, you're going left. But notice I can also use properties of exponents and think of this, the right side as b to the minus h times b to the x. Remember, properties of exponents, you keep the same base and add the exponents. So now b to the minus h is a constant, and I can multiply both sides by b to the h and get b to the h times y is b to the x. So now we can think of taking y equals b to the x and leaving the x alone, but this time replacing y by b to the h times y. So that means what we're really doing is dividing the y's by b to the h, or multiplying the y's by b to the minus h, and leaving the x alone, which is a vertical stretch. So it turns out that in this case, a vertical stretch is the same as a horizontal translation, which is kind of very unusual for a function to have that property. Okay, that would not normally happen, but it does happen for this particular kind of relation, which is a very interesting property that this has, very unusual property. Okay, so let's do this with some numbers in it for a specific example. If we think of y equals 2 to the x minus 3, we can think of that as taking y equals 2 to the x power, that should say, and replacing x by x minus 3 so that's a horizontal translation, shifting the graph 3 units to the right. So for example, 2, 4 would go to 5, 4, and 0, 1 would go to 3, 1. Okay, but you can also think of it as, remember, you can think of 2 to the x minus 3 as 2 to the x times 2 to the negative 3. 2 to the negative 3 is 1/8. So you can think of it as y equals 1/8 times 2 to the x. Well, thinking of it that way, you might think of it more in terms of replacing y by 8y. So this, in fact, even might write it in your head at least as 8 times y equals 2 to the x. So we've replaced y by 8y. So now it's a vertical strain, in this case a compression, so that it's 1/8 as far from the x-axis from every preimage to image point. So in this case, for example, again we start with the preimage of 2, 4. It's 1/8 as far from the x-axis, so we're leaving, yeah, this is wrong. Let's try this again. We want to leave the x alone, and we want to multiply the y by 1/8. So 4 times 1/8 is 1/2. And 0, 1, this is backwards, we want to leave the y alone, which is 0, and leave the x alone, which is 0, and divide the y by 8, or multiply by 1/8. There we go. So now it's 1/8 as far from the axis. Now here are both the graphs. The purple one is y equals 2 to the x, and the second one is the same graph whether you graph it as y equals 2 to the power x minus 3 or y equals 1/8 times 2 to the x. So you can think, for example, of taking this point okay, here at 2, 4, and just shifting it to the right 3 to 5, 4. And you take every point and shift it to the right 3, and you'll see that that works. Right, everything's to the right 3. But you can also think of it as leaving them alone and compressing them. So leave this point here, leave the x alone, and make it move down to 1/8 as tall. Here, 1/8 as tall, 1/8 as tall, 1/8 as far from the x-axis. So a horizontal translation by h is equivalent to a vertical strain by a factor of b to the h. So that's kind of an interesting factor. Wait a minute. It's actually this should say b to the minus h. No, not minus b to the h. B to the minus h. Okay, further notice that we can change the base, and that's equivalent to a horizontal strain, or to again to a horizontal strain this time. So if we have y equals b to the ax, we can think of that as y equals b to the a to the x, because remember our property of exponents says if you have a base to a power and then raise that to another power, you can multiply these two powers. Okay. So if we can think of this as replacing, if we start with just y equals b to the x, we can replace x by ax, which we know is a horizontal strain, a stretch horizontally. But notice that's equivalent to just replacing the base b with the new base, b to the a. Now, what this really allows us to do is to change bases. Okay? So, for example, if we have y equals 2 to the power 3x, that's y equals 2 to the third to the x, which is y equals 8 to the x. So we can change that. Or if we started with y equals 8 to the x, we could change to y equals 2 to the 3x. But notice what happens. We pick up a new coefficient in front of the x there. Now, this number e that we mentioned earlier, which is a very specific, naturally occurring, irrational number, okay, and we'll talk more about this later, but it turns out that e is the number we like to use for a standard base. Okay, so we can write y equals b to the x, but we can also write it as e to the kx. So when we change from any base b to base e, we pick up a coefficient on our x that we're going to call k, and I'm going to be consistent about calling that letter k. And of course, so you can see that this would be e to the kx is e to the k to the x, so we see that b has to be e to the k. Now, in a few sections down the road, we're going to introduce something called a natural logarithm, and so you can solve this last equation, e to the k equals b, solve it for k, and we see that k is the natural logarithm of b. That'll make more sense in a few sections from now when we define natural logarithms. Okay, now let's take some of these ideas and put them together. Well, it turns out that every transformed exponential function, we could write it this way: y equals a plus c times b to the x, where a, b, and c are constants. And all of these are all exponential functions are just transformations of one of these things where we have different a's, b's, and c's. So pick an a, b, and c, and any transformation you could do to any exponential function will end up being one of those. Now, a couple features here. Notice that if you plug in x is 0, b to the 0 is 1 times c is c, c plus a is then a plus c. So that y-intercept is 0, comma, a plus c. The horizontal asymptote, depending on the size of b, okay, either as x gets really big or really little, way to the right or way to the left, one of those or the other is going to make b to the x go towards 0. And so c times that's still going to go towards 0, and so the graph is going to go to the asymptote of y equals a. So y equals a is your horizontal asymptote. So we've shifted it from, remember y, this is basically replacing y by y minus a from our original graph. So if we started with y equals c times b to the x, and then replaced y by y minus a, we get this form, y equals a plus c times b to the x. And so now our horizontal asymptote is just y equals a. It's going to approach this on the left when the base is between 0 and 1. No. That's backwards. It's going to approach on the right if the base is between 0 and 1, and on the left if the base is greater than 1. The graph is entirely below the asymptote for negative c and entirely above the asymptote for positive c. Of course, if c is 0, then this degenerates down to just a y equals a, which is a constant function, not really exponential anymore. So we don't really want c to be 0. And remember, like we said before, the base needs to be either between 0 and 1 or bigger than 1. We don't want the base to be 1, because that would again give us a constant function. We don't want a base of 0 or negative, because that would give us some kind of weird thing that's full of holes, so that's not going to be anything that we want to mess with. Another way to write this is in terms of e. So we could always write this as y equals a plus c times e to the kx. Here I've just replaced b by e to the k, which is what it is. And now your constants, well, e is a constant, but it's a specific constant. It never changes. And it's kind of like pi. It's just a naturally occurring irrational number. But a, c, and k are constants, but they're parameters. They can change, and each time you change them, you get a different function. And so here we get y equals a plus c times e to the kx, where a, c, and k are some constants. Again, the y-intercept is 0, a plus c. Again, the horizontal asymptote is y equals a. Again, it's approaching on the right when k is negative, and on the left if k is positive. And the graph is entirely below the asymptote if you've got a negative c, and entirely above the asymptote for a positive c. Now, I have a GeoGebra applet called Graphing Exponential Functions by Sliders, and if you should pull that open and you can manipulate, it actually uses this last form here. A, C, and K are the things you can manipulate. But it also figures out what B would be, because it does e to the k and tells you what B would be. And it even figures out what R is, which is just B minus 1. And you can see what happens as you move those sliders. You can see what happens in the graph, and actually how different values of k, how they relate to the values of B and R as well. So what you should do now is open that applet and experiment with that a little bit and see what kinds of graphs that you get. It allows you to dynamically change those graphs.